Exercise number 10 asks us to evaluate the surface integral over S of xz ds, where S is the part of the plane 2x plus 2y plus z equals 4 that lies in the first octant. Minor bit of notational confusion that is potential here. The text often uses a capital S to indicate a surface, but a capital S is also used to indicate surface area. So this ds is a differential surface area of the surface S. It's kind of a clash of notation there, but hopefully that isn't too confusing. The idea is that we have a surface, this plane. We're only looking at the part of it that lies in the first octant. So let's get a handle on approximately what that looks like. So if we have x, y, and z, let's graph this thing here. Well, first off, if x and y are 0, we get z equals 4. Whereas if y and z are 0, then x equals 2. And similarly, if x and z are 0, then y equals 2. So it looks like we get something that looks sort of like this. This is our surface S. Okay. Now, this is important mainly just so that we can figure out what its projection is in the xy plane. We will be translating this into an integral over a two-dimensional region D. And we can see here that in the xy plane, we get something like this, right? So that looks like the line y equals 2 minus x. That'll be the domain D, sort of the shadow or footprint of this surface in the xy plane. We also need to know what z is as a function of x and y. So we have z equals, this is relatively easy to solve, 4 minus 2x minus 2y. Okay. Now, let's now look at what we'll need here. So we're turning the surface integral into a double integral of the domain D. We have x and z. We have an expression for z in terms of x and y, so we can expand that well. ds, the differential surface area, is basically the thing that we used to compute surface area back in chapter 15. We can take the partial of z by x and square it. We can add the partial of z by y and square that. Add 1, take the square root of all of that, dA. This is the differential surface area. So looking at what we have, partial of z by x is -2. Planes are nice because they're linear and the partials come out very cleanly. The partial of z by y is also -2. So it looks like we get 4 plus 4 plus 1 dA. 8, 9, that's a square root of 9 dA, so we get 3 dA. Generally speaking, when we work with planes, we will get some constant times the differential dA. We were fortunate that this didn't even have a radical at the end, so that's good. Now we kind of have all these pieces, and we can just start sort of plugging things in. So let's see here. We have the double integral over S of xz ds. We have the double integral over S of xz ds. So now we can translate that to the double integral over D of x times z. Z is 4 minus 2x minus 2y times ds. ds is 3 dA. So if we start writing this a little bit more explicitly here, so we have, first off, glancing through, we see there's a constant 3 we can pull up front. We have a double integral over D that will turn into an iterated integral in just a moment. We can push the x through here. There's no reason to leave it out here since this factor also includes x, so that doesn't mean this is separable, so we may as well distribute it. 4x minus 2x squared minus 2xy. Looking at what we have, the most obvious way to write this was y as a function of x. We could have written x as a function of y instead. Let's just leave it this way. This is the obvious way to do it. So we'll have dy dx as y goes from 0 to 2 minus x, while x runs from 0 to 2. And now you see I've written this as at this form. This is a relatively simple iterated integral from early chapter 15. I shouldn't say simple, easy. It's easy. It's not necessarily simple. You get, when you integrate this, you get a polynomial you have to distribute. So it takes a few steps, but you can work through that on your own and confirm in the end that this works out to 4. So really, surface integrals, once we figure out what the... actually, basically a surface integral problem is very much like a surface area problem from chapter 15, 15.5 I think was the section, except that you have another integrand here that you stick in, right? Everything we did in terms of figuring out what was under the surface and computing this square root, remember this is just the surface area. So if we're taking a surface integral over a scalar field, so our integrand is just a scalar, then it's just like evaluating the surface area, except that you also have to stick in whatever that expression is. And that's about it.